Hello, hello. We will continue with the volume of rotation and the washer method. This time we're going to discuss case 2. We call case 2 a special case. You're going to know why. So for case 2, we have the region that is described as the above. It's bounded by y equals f of x, below by y equals g of x, on left side by x equals a, and to the right by x equals b. By this time, the line of rotation is with respect to the x-axis. As you can see, mark the line of rotation. And because you can see there's a space between the region and the line of rotation. So that basically tells us we need the washer method. So because this is the line of rotation, the cross-sectional line for the washer method is also perpendicular to the line of rotation, just like the disk method. Okay, so the cross-sectional line is perpendicular to the line of rotation. So if you project this cross-sectional line, it's going to touch the x-axis at x. So that basically that tells us everything here must be expressed in terms of x. So the line of rotation, so the bottom end of the line of rotation, okay, the bottom end of the cross-sectional line to the line of rotation is the inner radius. The top end of the cross-sectional line to the line of rotation is the outer radius. So let's look at the inner radius. So the inner radius is this point minus this point. So this point is the curve y equals g of x. And this point, since it's the x-axis, the equation the x-axis is y equals 0. So you have y equals g of x, and then y equals 0. So we're going to take a g of x minus 0, which will give us a g of x. So that is the inner radius. The outer radius, you go to the top end point of the cross-section line minus the point that is on the line of rotation. So this point basically is y equals f of x, and we know here at the line of rotation is y equals 0. So the distance between so the radius is going to be f of x minus 0, which just gives us f of x for the outer radius. Okay, so now that we got that, we can now go to we did step 1, we graphed, and then we go to step 2, inner radius. We copy this down, which is g of x, and then we go to inner area. So inner radius, inner area, basically pi times g of x squared, and then we go to outer radius, which is r sub 0 of x equals f of x. The outer area is going to be a sub o of x is going to be pi times f of x squared. The area of the washer, a sub w of x, is going to be the outer area minus the inner area. So you get pi times f of x squared minus pi times g of x squared. You can factor out the pi to get pi times quantity f of x squared minus g of x squared. So that's the case where you have the rotation with respect to the x-axis. So let's look at the example. Okay, and then the volume of the rotation is where we're going to integrate the area of the washer and a sub w of x, and that gives us the volume of rotation. So let's do an example here. So here they give us the region to be bounded by y equals x and then y equals x squared, and the rotation is about the x-axis. So step 1, we graph the region. So you graph y equals x squared. It's a parabola that opens up with vertex at 0, 0. The y equals x is the identity function, which is a straight line that goes through 0, 0, 1, 1, and so forth. So the two curves give us this region. And and then the line of rotation is with respect to the x-axis. Okay, so we put those curved arrows there. So now the question is to find the inner radius and the outer radius. So we draw our cross-section line, and so the bottom end of the cross-section line to the x-axis is the inner radius. So this bottom end is the function x squared, y equals x squared, and at the bottom at the x-axis we have y equals 0. So the inner radius is going to be x squared minus 0, which is just x squared. And when you look at the outer radius, so we have this top point of the cross-sectional line, and then minus the point on the line of rotation. So this point is y equals x, and we already know this is y equals 0. So the outer radius is going to be x minus 0, which is x. Okay, so now we got the inner radius, which is x squared. So we found the inner area, which is pi times inner radius squared. So it's going to be x squared squared, which will give us x to the fourth. And then we write down the outer radius, which is x, and then we find the outer area, which is pi times x squared. So we get the outer area, and we find the area of the washer, which is the outer area minus the inner area. So it's going to be pi x squared minus pi x to the fourth. You can factor out pi to get pi times quantity x squared minus x to the fourth. And now we need to integrate the area of the washer, but we need limit of integration because it's not really given. Okay, so we know based on the sketch, the graph of the region is bounded. It's going from x equals 0 to this point of intersection here. How do you find this point of intersection? This is where the two curves meet. Okay, so at this point the two curves have exactly the same point, the same values of x, same values of y. So to set it up, we're going to set the two functions to be equals. So we're going to set x squared equals x. Okay, so I kind of did it here. So x squared equals x. Then you add x, you subtract x to both sides, you get x squared minus x equals 0. You factor out x, you get x times quantity x minus 1. You set x equals 0 and then x minus 1 equals 0. So that gives you x equals 0 and then x equals 1. So a is 0 and then b is 1. And then we go to step 6. So we have our limit of integration. We're going to integrate from 0 to 1. And we're going to integrate pi times quantity x squared minus x to the fourth. Pi is a constant. You can move it outside of the integral, and then you just find the antiderivative of x squared, which is x cubed over 3, minus the antiderivative of x to the fourth is x to the fifth over 5. And then you can evaluate this at 0 and 1. So when you plug in 1, you get 1/3 minus 1 over 5. Minus, when you plug in 0, you get 0. So you end up with v equals 2 pi over 15. Okay, so that's the end of case 2. Next is case 3. Thank you.